Okay, today we're going to look at Lesson 21, and your I can statement or learning objective is I can identify points of discontinuity. I always want to say that wrong. Discontinuity in rational functions. So you're going to notice that the name of your assignment today is Rational Expressions Mixed. So most of the problems are things that we've already done. So adding, subtracting, multiplying, and dividing rational expressions. Okay, that's what we've been doing in lessons 18, 19, and 20. So none of that is new. And you can look back at old videos or previous videos and previous homeworks for examples and practice problems of those types. Okay, but there are a few problems at the beginning of the assignment that deal with some vocabulary and some concepts that we've kind of hit on but not talked about specifically. So that's what we're going to focus on today. We're just going to look at the first part of your assignment. I'm going to explain it to you, talk about what points of discontinuity are, and then the rest of the assignment, like I said, is review stuff that we've already done. Okay, so we'll go ahead and get started, and we're going to talk about what a point of discontinuity is. Okay, so a point of discontinuity is just a break in the graph. We are switching from expressions to functions here. So when we have a function, it's set to, with y equals or f of x equals, and then we can solve it and we can graph it. Okay, so a point of discontinuity is just a break in the graph. So that means that at that point in the graph, it's not continuing, it's discontinued. Okay, it's not just a continuous line. So we get a break in the graph from any excluded value. So before, when we were simplifying rational expressions, we had those restricted or excluded values. Remember, you set the denominator, the factors in the denominator equal to 0, and figure out what x or your variable cannot be. Those are excluded values. And so we know we get excluded values by looking at what would make us divide by 0. So we set the denominator equal to 0 and solve. Okay, so a point of discontinuity is just a break in the graph or any excluded value. So we've talked about that. We've talked about restricted values. We've looked at them. We've pointed them out. We've written them down. We've typed them in Math Excel. So now we're just looking at how those behave in the graph as points of discontinuity. Okay, when you get excluded values, so when we find our restricted values or what would make our expression divided by 0, we have two different types. So two different types of excluded values. They can either be a vertical asymptote or a hole in the graph. Okay, so I'm going to show you what a vertical asymptote is and what that means, and then we'll look at how you figure out if your excluded value is a vertical asymptote or a hole in the graph. Okay, this is what a vertical asymptote looks like. Okay, we've got our coordinate plane, and we have this dotted line at x equals 3. Okay, I'll write that over here. So at x equals 3, we've got this nice dotted line. That's a vertical asymptote. And if you notice, our graph, the curves, get extremely, extremely close to that line, but they never touch it. Okay, and that's what an asymptote is. It means that the curve or the graph is going to get very, 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 very close to that line, but it will never get exactly on it. Now, when you're looking at a graph or you're doing a sketch, sometimes it might look like the lines touch just because you can get so close. Like you can go to 0.2999999. You're just not going to get to 3. So they get extremely, extremely close to this vertical line, but they don't touch it, okay? Okay, so your excluded value is a vertical asymptote if you can't cancel the 0 or you can't cancel that factor, okay? Because that's what we're looking at them as. So if you can't cancel it out or divide it out, then it's going to be a vertical asymptote, and that means that your graph will get really, really close to that line but never touch it. All right, now your other option is just a hole in the graph. And so that means that there's a hole in the graph, that there is a point where the line does not go, and it's just like a little missing spot, a little hole. Okay, So that hole that we're talking about, that hole in the graph, it's 1 pixel in your calculator, okay? So that means it's so small that we won't see it. Just like I was saying over here with the asymptote, you can get super close, like 2.99999, but you won't be right on 3. The same is true with a hole in the graph. So if you have a hole at +2, then you're going to have, the line's going to go all the way up until that exact point. So the 1/1,000,000th decimal before and the 1/1,000,000th decimal after, there's going to be points there. Those are going to be covered, but just this one teeny tiny little point will not. And so we're not going to be able to see that with our eyes. We're not going to be able to see that in our calculator, which is why we have to find these by hand using our algebra, okay? So the vertical asymptotes, if you graph the problem, you'll be able to see those vertical asymptotes, but you will not be able to see a hole. So we have to do that algebraically, the way I'm going to show you in just a second. And so we get a hole in the graph, or we know that our excluded value is a hole if you can cancel the 0, okay, or that factor. So what we're going to do today is very similar to what we've been doing. We're going to factor the numerator, factor the denominator, find our excluded values, or our points of discontinuity, and then we're going to decide if each one is a vertical asymptote or a hole in the graph. So if it cancels or divides out, it's a vertical asymptote. If you can't cancel it or divide it out, it's a vertical asymptote. If you can, it's a hole in the graph. Okay, so now we'll just look at some examples. I'm going to go right to the some sample problems from your Math Excel work and work through those. Okay, so number 1, it gives us this function, and remember, it's a function now, so we have y equals, okay, that makes it a function, and we need to find our points of discontinuity. So we're going to factor it. On the top, we can't really do anything, it's just x plus 3. On the bottom, it's going to be x plus 3 and x plus 5, okay? So first, I'm going to identify my points of discontinuity, okay? And I'm just abbreviating because I don't want to write out those words. Okay, so the point of discontinuity. So x equals -3. So x is not allowed to be -3. Remember, it's the opposite of what it looks like. And then x equals -5. So those are our points of discontinuity. All right. And just for fun, okay, just for fun, we're going to decide which one's an asymptote and which one's a hole in the graph, okay? So we can go ahead down here and choose your answers. We have A and we have D. Remember, we're finding it's X, okay? We're setting these factors equal to 0, so it's going to be X equals something, not Y. So you can go ahead and eliminate those options that have Y, okay, because your point of discontinuity is never going to be Y equals, okay? It's going to be X equals. All right, so if I was going to simplify this, I could divide out my x plus 3's, and so that means that this would be a hole in the graph, and then x equals -5 can't divide out or can't cancel, so that's a vertical asymptote, okay? And I'm going to show you what that looks like on the actual graph, okay? All right, so I've graphed this problem in my Inspire calculator, and you can see this nice curve and this nice curve. And so we decided that x equals -3 is a hole and x equals -5 is a vertical asymptote. So if we go to -5 on the graph, you can see if we were to draw a line, okay, these curves of the graph get extremely close, but there's never anything right on -5. So we got that. That's correct. Okay, now x equals -3. If you go to -3, it looks like the graph is there. You don't see anything awry. So that means that it's just a hole in the graph. And remember, like I said, it's so small, you can't see it with your naked eye. So to us, just looking, it looks like nothing's there, okay? Or nothing's happening there. It's just the regular graph. And so that's a good way to identify that this point is a hole in the graph and not a vertical asymptote. So if it's a vertical asymptote, you're not going to see anything there, okay? If there's a hole, it's just going to look like the graph is going on. But you just have to know we can't see that little missing piece. All right, number 2, find the vertical asymptotes of the graph of the rational function. So this one, there's no simplifying to do. You're just finding the vertical asymptote. So x equals, what's the opposite of that? Negative 16. So the equation, okay, I'm sure it's equation of the vertical asymptote is x equals negative 16. So that's all you have to do on that one. Super, super easy, okay? Number 3, find the vertical asymptotes and holes in the graph of the rational function. So first, let's find our points of discontinuity. All right, so we have x equals 2 and x equals negative 7, okay? Can either one of those divide out? Yes, the 2's. So the 2's, those zeros, those factors cancel or divided out or canceled out. So that means that there is a hole in the graph. So x equals 2 is a hole, and x equals negative 7, it couldn't cancel, so that is a vertical asymptote. Okay, number 4 is the last one that we're going to look at together before I let you go on your own and do some work. So it says sketch the graph of the rational function. There are a couple different ways that you can do this. 1, you can type it in your calculator and see which graph matches. 2, you can use what we know and look for the vertical asymptote and the horizontal asymptote. And I'm going to show you how to do that real quick as well. And that's a little bit different. And we don't really talk about it much. We're not really going to talk about it anymore. You'll see it when you get to pre-calculus if that's where you're going. But just for analyzing graphs, maybe on the ACT, it might be helpful if you don't want to use that calculator. Okay, so we know x equals negative 3 is an excluded value, and it can't cancel out or divide out, so that's the vertical asymptote. So we're going to find x equals negative 3. Let's see. So it's right here on the graph. All right, so we can cancel out all the ones where the curve touches that little mark we made. So that's going to eliminate A and D. All right, so now we just have to decide between B and C. So to find a horizontal asymptote, you take the leading terms of both the numerator and the denominator, and you simplify them. So x over x simplifies to 1. Okay, so that means we're going to look for where y equals 1, and that's going to be the horizontal asymptote. So this is y equals 1, and this is y equals 1. So again, if it's an asymptote, the curve can't touch it. So that takes out B, and our answer is C. Okay, so if you did not want to use the calculator, you don't want to type that in, that's how you can find the vertical asymptote like we've been doing. And then the horizontal asymptote's a little bit different. But if you know what to do, it's pretty quick, and it can help you narrow down your graphs pretty easily. Okay, so like I said, the rest of your problems are review, add, subtract, multiply, divide, rational expressions. So you should be good there. But if you have any questions or need any help, just let me know. Have a great rest of your day.